Suppose x1 through xp are some input variables. We can represent these as follows: x1 through xp. Okay, we'll call these input units. Okay, and together they form the input layer. Okay, the input layer of the neural network. We include one additional input unit consisting of the constant 1. Okay, this additional input unit is called a bias unit. Now, suppose we take a linear combination of the input units, so alpha 0 times 1 plus alpha 1 x1 plus dot 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 plus alpha p xp. Okay, letting alpha be alpha 0 through alpha p and x be 1 through 1 comma x1 through xp. Okay, we can rewrite the linear combination here. We can rewrite that as alpha transpose x. Okay, so thinking of alpha as a column vector, we take the transpose, which will give us a row vector, multiplied by x, which is a column vector. That will give us this linear combination here. Such a linear combination is called an activation. Suppose we then took h of alpha transpose x, where h is a differentiable, possibly nonlinear function. H is called an activation function. Suppose we form m such activations, ai, given by alpha I transpose x, where alpha I is this, alpha I0, alpha I1 through alpha IP, and I ranges from 1 to m. Taking h of each activation ai, we get zi, given by h of alpha I transpose x, for I equals 1 to m. We can represent the zi as follows. Okay, z1 through zm. And here, remember the alphas, those were the weights in the linear combinations that we formed to get the zi. So this line here, we'll put alpha 1 0. So that means we're going from z1 to x0, okay, which is 1. Okay, alpha m0, we're going from zm to x0, and alpha 1 1, we're going from z1 to x1. Alpha m1, we're going from zm to x1. And similarly for alpha 1p, we're going from z1 to xp. And alpha mp, we're going from zm to xp. Okay. The zi are called hidden units. And together they form the hidden layer of the neural network. The alpha sub ij's are called weights. Okay. Again, we include one additional hidden unit consisting of the constant 1. We could continue this process of creating more and more hidden layers, but we won't for now. Now, suppose we take a linear combination of the hidden units, okay, beta 0 times 1 plus beta 1 z1 plus dot 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 plus beta m zm, letting beta be this and z be the vector consisting of 1 z1 through zm. We can rewrite the linear combination as beta transpose z. Suppose we form k such activations, b sub k, given by beta k transpose z, where beta k is this vector and k ranges from 1 to big K. Suppose for a fixed k, little k that is, we applied some activation function g sub k to the vector of activations b1 through bk to get yk given by g sub k of b1 through bk. Suppose we have such activation functions g sub k for each k ranging from 1 to big K, and that we defined y sub k in the same way here. We can represent the y sub k as follows here. So we have y1 through yk, and similarly we draw the lines connecting the hidden units to the yi, or the y sub k. The y sub k are called output units. And together they form the output layer. The output layer of the neural network. Writing out y sub k equals g sub k of b1 through bk, more explicitly we get this, where b sub k is given by beta sub k0 plus the sum beta ki zi, as I ranges from 1 to big M. Okay, and that's equal to the sum beta ki zi as I ranges from 0 to M, if we let z0 be 1. Okay, and zi is given by h of alpha I transpose x, so this is just equal to this as long as h of alpha 0 transpose x is equal to 1. Okay, if we just let h of this alpha 0 transpose x be defined as just 1. Okay. Now, this part here is alpha 0 plus the sum alpha ij xj, j ranging from 1 to p. Okay, and we can rewrite that as just the sum as j ranges from 0 to p of alpha ij xj if we let x0 be 1. Okay, so b sub k is given by this. Okay, so b sub k can be seen as a composition of linear functions, the linear combinations, and possibly nonlinear functions in an alternating fashion. More explicitly, we're taking linear combinations of x1 through xp and of the bias unit x0 and applying the activation function h to them to get z1 to zm. We're then taking linear combinations of z1 to zm and of the bias unit z0 and applying the activation function g sub k to the collection of all of them to get y sub k. Okay, so here we have y sub k is g sub k of all of them, b1 to bk, big K, where b sub little k is given by what we just found here. Okay. The network diagram we constructed has a single hidden layer, and the corresponding neural network model is called a single layer perceptron. If there are multiple hidden layers, the corresponding neural network model is called a multi-layer perceptron.